Hello everyone, welcome back to Linked Frequency. In this tutorial, we are going to learn about how to design a DC to DC buck converter circuit using LM2596 IC. I am Vaibhav Sugandhi, passionate PCB designer and technology startup founder. This is the 17th tutorial of practice project for PCB designers, and here I am going to present you a new way of designing or a new technology being involved in our practice project. Till here, we have learned how to design a product in electronic industry by using a black box analysis, white box analysis, datasheet analysis, and by starting with a morphological chart and selecting a components, designing a circuit on a paper and referring a datasheet to understand how they behave, doing certain calculations if required, and then jumping into the schematic activity. But right now, here and after, for the next 3 to 4 projects, whatever we are going to do in this tutorial series, we are going to use the datasheet directly to create a circuit diagram. I'm not going to present a black box analysis and a white box analysis and datasheet analysis, maybe a datasheet a little bit, but not black box and white box. Why? Because I believe that you have understood how to do a black box analysis and a white box analysis by yourself. And I want you to try it by yourself and experiment how to create those black box and white box without having a requirement of any assistance. That's where you learn the designing process, or that's where you acquire the skill of designing any circuit by yourself. Now, in this tutorial, I am more focusing on using this LM2596 IC, which is SMD in nature. Right now, I am considering SMD IC, but also it is available in a through-hole component. But however, in this tutorial series, I am considering to redesign this entire buck boost or buck converter module available in market. It will be a very easy and very simple one with a very few components, like hardly 7 to 8 components in the entire circuit, only 2 mounting holes. We are going to use the same architecture what is visible in front of you in this PPT slide. So let's get started with the datasheet analysis of LM2596. Here we have a datasheet of LM2596 simple switcher. It is so called a switcher by the company Texas Instruments. It is a power converter with a 150 kilohertz frequency of switching. That's why it is so called switcher. Why it is so called a switcher or a power converter with a 150 kilohertz? Because it converts the unregulated DC voltage or any kind of a DC voltage into another level of DC voltage. If it is a buck converter, then it reduces. If it is a boost converter, it increases the voltage. However, it converts from one level to another level by means of switching or turning on and turning off the MOSFET inside as well as inductor outside. By using these two components, it will turn on and turn off, turn on and turn off the inductor by using a MOSFET inside, because of which at a certain frequency it turns on and turns off, turns on and turns off, because of which it will regulate and convert the unregulated DC voltage or another level of DC voltage provided at the input side. Let's discuss about it in more with respect to this datasheet. If I scroll down, you will learn the description or the exact meaning of what is the switcher or the buck converter in a detailed way according to this IC manufacturer. And this is a 3 ampere output load current capable switching IC, or maybe a regulator IC. You can say SMPS IC it is. So make sure that you understand what is this 3 ampere. That means it is a maximum possible load current will be 3 ampere. Beyond 3 ampere, it doesn't work and it starts heating and simply it breaks down after certain current level, which is given in the absolute maximum condition level. And it has a various features which are essential for any kind of industrial design. And of course, this particular product or this particular IC we use for most of the product that we design in our company, whichever requires a 3 ampere of a current rating with a 5 volt of output DC voltage, most of the cases in fact. So that's why I'm recommending, or maybe I'm demonstrating how to design a circuit in easyEDA by using this particular IC. And if you scroll down, it is available in 2 package. One is a TO220 package, which is through hole technology, and TO263, which is a KTT package, which means it's a SMD component. So I'm focusing on the SMD side right now, but you can use it for through hole also if you're not comfortable with the SMD. Thereafter, you can see here the applications are various applications available. In most of these applications, not only these, most of the other applications, we use this particular circuit. And this is how the typical application looks like. This application is for 5 volt regulated regulated DC output voltage, wherein the 12 volt unregulated DC voltage has to be given at the input side. If you want a variable, then you have to add one variable resistor along with this particular circuit, so that you can control the output voltage with this feedback button. So I mean the feedback pin actually. This feedback is going straight from the output voltage. You have to add a voltage divider circuit here, so that you can control the output voltage however you want it. Thereafter, if you go down here in a list of content or a table of content, you can see that lot of information is given with respect to this particular device. You have to understand all these information before designing a professional and industrial grade buck converter. However, if you are starting with this design, you need not to understand everything. Just go through this entire data sheet, understand how exactly the electrical characteristics are looking like, what is the minimum input voltage and what is the maximum input voltage, minimum current and maximum current with respect to output, which is a load actually, and how the ripple voltage looks like, and what is the efficiency looks like. All these details are good to have or very essential to know as a hardware design engineer. So always study these and remember them. What is this 80% means actually, and what is the difference between this one and your linear voltage regulator, which is 7805, right? 7805 has somewhere around 41% or 42% efficiency, very low and very outdated in industry. However, this one is 80% efficiency. Still, it is not good one. Again, we have a 95% efficiency buck converter in the industry, but they are too costly. That's why we go with this one as 80% is sufficient, much better than the 41% or 42%. And if you go back to the table of content, you can see a lot of information given here: mechanical, packaging and orderable information, and also a device and documentation support and application implementation, how you want to implement application. If you go here, how to select the input capacitor, given in entire detailed explanation here. And maybe if you scroll down, by using this particular graph, you can decide what is the capacitor value you want to use for the input side of the entire circuit. Output capacitor is also given here with the graph, and then what type of a diode to be used in this entire circuit. And then we have inductor selection process. Inductor selection is also very important and very minute detailed design, which you have to understand in case of buck converter or boost converter. So these all things are very complicated to explain in this small video, so that's why I'll leave all these things to you. You just go through and read all the document inside this particular data sheet, or all the information inside this particular document, so that you will understand what exactly the meaning of hardware design engineering with respect to the buck converter. Now it's time to jump into the schematic design and start with the schematic as we always do. So let me jump into the easyEDA, start with the design activity. All right, now you can see that this is how the entire schematic is designed. First thing is this IC schematic symbol is not that great, but anyway, we are using it just because we are running out of time in this video. However, you can notice that I have connected a single pin connector for input Vin plus and Vin minus, or plus Vin plus minus Vin, and similarly for a plus V out and a minus V out. Why? Because in our PPT, which you have seen, that we want to literally replicate the dimension and the placement of the component as per this particular module which is available in industry. So first thing is, you can see this pin is here and this pin is here. It's not a connector actually, it is a corner rectangular connector which can be used as a wire harnessing point, or maybe connecting a jumper wire over there. Only a single pin, not multi-pin or a 2-pin with a certain pitch or a dimension or something like that. That's why we are literally going ahead with the copying this particular design which is available in the market. Now that is also not replicated in the datasheet, which you have to understand and replicate it in your design. That's why this part is something special you have to understand in your entire project here and after, or maybe again and again whenever you are designing such kind of application. And thereafter we have inductor footprint we have not finalized. Why? Because this particular inductor, the size of this inductor and the footprint and kind of a part number of this inductor is not known to us right now. Let us find if it is available in datasheet. Application and implementation. So let's go to the inductor section, input capacitor it is, and if I scroll a little bit down, you can see inductor selection here. Yes, and do they recommend any specific inductor for this? I hope they 22 microfarad. Oh, all right. We have a lot of inductor selection here. Of course, we have this one, 220 microfarad is something that we are looking for. In fact, in our design, we have used, not 220, 33 microfarad. So this one, 33 microfarad through hole. Okay. So I think we have a pulse engineering, that inductor part number is given, through hole is here and surface mount is here. So Coilcraft is a one company which has the only surface mount inductor and its part number is given here. This is wonderful actually. That's why we need to use a datasheet. I hope you understood right now what is the importance of datasheet. So in datasheet, they have recommended us several different companies inductor for through hole as well as surface mount. It's absolutely a piece of cake for the designer. Why? Because we need not to search the whole internet to arrive at this part number. They are already given. As a manufacturer, they are already given this part number. Let's search about that particular inductor in our global library. If at all available. I think it is available, but I don't think so it is available in the way that we want. What we can do is we can copy or we can understand this footprint. You can see that this footprint is same for a different part number also. 3316333 is the our part number, but DO 3316472 is the inductor available in the global library right now. What I can do is I can bring that inductor, place it here and use that footprint. I mean, this is the jugaad way, but yeah, that's what we can do here. So we want this footprint only, not the symbol. So I'll go to my inductor. I'll just search this inductor footprint here and I'll just make sure that it's available here. And second one, does it look anything better? I don't think so. Both are better. So let's go with the first one only. Let's not spend too much time on that. 33 microfarad inductor, and I'll go and double click here. Boom. My inductor is now having the footprint of the recommended inductor in the datasheet. So this is how the datasheet is used, and this is how the entire circuit is designed with the help of datasheet. I hope you understood. Now let's jump into the designing the PCB. I'll go to the design, convert schematic to PCB. Now it is here. So I'll just go with a 2-layer PCB design because it is a SMD component, and start with 0,0. And width and height, we have to literally copy the dimension of this particular part from the internet. Right now, I don't know the exact dimension of this. I assume it is going to be somewhere around 10 centimeter or maybe 20 centimeter by 40 centimeter. Not centimeter, mm actually. Centimeter will be too much. So 20 mm by 40 mm. I assume that, and I'll go with that. So 20 mm by 40 mm. If it is not sufficient, I'll change it later on. All right. It looks like it is the correct one, but still what I will do, I will change the dimension. Go to this width should be 40 and height should be 20, so that I can design it very easily. Otherwise, I have to rotate the design and do it in this circuit. So I'll just select all the components, bring them this side, and I'll save this. I hope it is possible to do it in this dimension. Let's start with that. Alright, now you can see that this entire project is complete. First thing is, this project is absolutely awesome one, and this is something which I have not taught online till now in our linked frequency, or maybe with any students I have trained online. So that's why this is very special project for me as well, and I believe it is special for you as well. First thing is, we have completed our entire routing process in our single layer only. A top layer copper is sufficient for doing a complete routing activity for the entire circuit diagram, because circuit is absolutely simple. The second important thing is, even though it is completed in the single layer, I have added a ground plane for the ground reference, or maybe the bottom layer of copper for the ground plane reference. Why? Because these kinds of power modules or the power converters require very good stability with respect to ground, and to bring this stability we need to add a bottom copper as the ground layer as well. Along with that, if you want a thermal stability for this IC, we need to add these grid of wires which will connect the ground part of the top copper with the ground part of the bottom copper. That means bottom copper itself is treated as a ground, and the top copper is also treated as a ground, because this body of this IC is a ground pin actually. So that's why we have added a grid of wires here. These wires are tinted wires in the sense, if you go to the photo section, you will see that these are all normal wires only. They are not anything special. The normal wires which we use for the jumper, or which we use for the creating a connectivity between the top copper ground plane and the bottom copper ground plane, the same wire I am using here. Because the pad is exposed, should be exposed, because we need to solder a body of the IC, right? Because of that, these wires are looking like a untinted or not tinted wires. However, do remember, these are the normal wires which we are using. First thing. And the second thing is, we can notice the 2D visualization of this PCB is approximately, or accurately, I'm not sure on that, but approximately, I believe so, equal to the product available in market. Of course, it has one variable potentiometer here. Why? Because this particular product is a variable DC to DC buck converter, wherein my design is a plus 5 volt DC to DC buck converter. I have not mentioned plus 5 volt here and a minus or a ground here and a VIN here. I hope you will do it by yourself. And this is how the 2D model looks like. And if you go for the 3D model, this is how awesome it looks like. So I think this is the first SMD, complete SMD project which you are going to do in this entire tutorial series. I hope you will love it and you will enjoy the process. Maybe you can post it on LinkedIn, or maybe on your WhatsApp, tagging our linked frequency on LinkedIn available now, and you can share your experience of learning how to design these products using easyEDA by this particular tutorial series. So thank you so much guys for watching this video. I believe you understood the entire process, and I hope you understood how exactly the products are designed in the market or maybe in the industry. And I also believe that you understood how to create a black box analysis, white box analysis and datasheet analysis before jumping into the schematic design. If you have any questions regarding any part of this entire tutorial, feel free to comment in the comment section below. I'll answer as early as possible from my side. Thank you so much for watching this video guys. See you again in the next video. Until then, tune yourself to make a difference.